ASC and defended it on December 2005. The title was Interaction of Massive Stars and the Interstellar Medium in H2 regions and under the supervision of Artemio Herrero and César Esteban. Then he went 1 year as a support astronomer at the ING, specifically at the INT telescope. Then with a postdoc from the Spanish Ministry of Education, he went to Paris to work with Gracina Stasinska and to Geneva to work with Daniel Scherer. And then he came back to the ISC about a year ago, and he's now working as a postdoc in the Flames 2 survey of massive stars. And without any further notice, I'll leave you with Sergio.
Gracias. First of all, thank you very much to everybody for coming. I'm going to present you a very recent result. The paper has just been submitted 2 weeks ago, and it's about the chemical composition of the Orion star forming region. I will talk about B-type stars, gas, and dust. Okay, this everybody knows the Orion constellation. The Orion star forming region is located here. Is one of the closest star-forming regions, along with Perseus OB1. It contains the Orion OB1 association, that is a group of O and B stars located in all this region here. Several studies a long time ago discovered that this association could be separated in different subgroups with different positions in the sky and different ages. So we have here 2 references, and the idea is that we have the older population, older subgroup here, and then the age is increasing that way, and then here we have what is called the Orion OB1 1D, that is the Orion Nebula cluster. We have also here the Orion Nebula, the well-known Orion Nebula, and inside the nebula we have what is called the Trapezium cluster. Since it's one of the closest star-forming regions, has been studied a lot, and for example, one of the things we can do in this region is to study the chemical composition. So for example, we have this paper by Cunha and Lambert. They derive abundances of different elements in B-type main sequence stars. So these are not evolved giant objects in the different subgroups, and this figure summarizes the results. So you can see that the abundances, the oxygen abundances they obtain seems to be lower in the older group and then higher in the younger group. So they propose that this could be evidence of pollution of elements produced by supernovae type 2, which affect the composition of the new stars, new born or new form stars. So this is why the oxygen and also silicon magnesium in these stars is larger. Another source of information we have about abundances in this region is the Orion Nebula. This is probably one of the most studied H2 region. You can find a lot of studies. The more recent one is the one by Cesar in 2004. They obtain a very deep good quality spectrum of the nebula, and they could not only see the collisional exciton lines, but also the very, very fine recombination lines. These are the results they obtained, so 8.51 from collisional exciton lines and 0.15 larger from the recombination lines. This is a well-known problem, so it's this difference between the abundances derived from both type of lines is known a long time ago, and the thing is that still is not clear, or the different people working on this is not in agreement about which one are the correct abundances or what is producing this discrepancy. Okay, one thing we need to take into account, because now I'm going to compare these abundances with the stellar ones, is that from emission lines you can derive only gas phase abundances, and you need to take into account that some of these, for example, oxygen can be depleted onto dust. So, for example, in 98, Cesar derived this amount of dust depletion, oxygen depletion onto dust. So the value they propose finally for the gas plus dust is this value here. Okay. One very important thing is that the photospheres of these B-type stars are unevolved objects and are very short time lived in terms of stellar evolution, must be the same as the abundances or the chemical composition of the interstellar medium from which they were formed. So we can compare the abundances derived from these two methods to see what happened. So, for example, here I plot the values derived by Cesar Esteban from the recombination and the collisional excited lines, and this is the value they propose when they took into account the dust. This is the mean value of the abundances in the B stars, so it seems that it's coherent. However, there are a few things we have to comment here. The first one is that the stars inside the nebula has very high abundances, so the comparison between these abundances and this one is not very good. Also, the mean value is okay, but this is not very good. And the other thing is that we cannot claim about any final conclusion because we don't know the amount of dust we have. So we can have more abundances and more dust, or abundances and a lower amount of dust. Okay, from 94 to now, there has been a lot of improvements and a lot of development in the stellar atmosphere codes of massive stars. This has been thanks to the improvements in the computational methods, the increase of the efficiency of the computers, and also the efforts devoted to the compilation of atomic data sets. So now we can count with fully line-blanketed non-LTE codes and two possibilities: the plane parallel model and also those other models with expanding spherical geometries. So you have here the Lusty is the one of the plane parallel, and here you have three extended codes. In comparison with the previous ones, we have that these were plane parallel. Either could be hydrogen and helium in non-LTE, or with the inclusion of the effect of line blanketing, but in LTE. Okay, so with these new models, Artemio proposed me for my thesis to study some of the stars in Orion to see what was the effect of these changes in the stellar model. So we did analysis of different stars, and three of these stars were B-type stars, so we could derive abundances, and this is what we obtained. So our abundances are here, so the difference is huge, and this is very important. The first thing is that, okay, if the abundances are here, then this possibility about the supernova type 2 contamination is not so clear. And then the other thing is also we say that these values here are in agreement with the recombination lines. Again, we have to take into account the amount of dust that is depleted on dust, the amount of oxygen, I mean. Okay, so what is the new things, the different things between the study of Cunha and Lambert and our study? First, I want to describe briefly the general overview of how we calculate abundances. That is, this is the last step. First, we need a spectrum, and then the stellar atmosphere codes, The stellar atmosphere codes are divided in 2 steps. The first one is the stellar atmosphere model calculation, where we obtain the structure of the atmosphere. This can be done in LTE, in non-LTE, accounting for line blanketing and different hypotheses. And once we have the stellar model, the stellar structure, we can compute the line formation code to obtain the line profiles and the equivalent width, and this can be done again in LTE, in non-LTE. Once we have this, we can create grid of models, changing the different parameters, the stellar parameters, the effective temperature, the gravity, abundances, and one parameter, free parameter that is in microturbulence. And then if we compare the observed spectrum with the models, we can first derive the stellar parameters. For this, we can apply what is called the spectroscopic approach, in which, well, I will comment about this later, or photometric calibration. If we decide to do this, we need the photometric data. Once we have the stellar parameters, so the structure of the atmosphere is well defined, we can do the line formation and obtain the abundances in this model atmosphere. Okay, so the differences, the first one is related with the type of stellar atmosphere codes. So Cunha-Lambert did it in plane parallel LTE line blanketed models, and then the line formation in LTE, and also did some non-LTE calculation. Also they say that they trust more these values because the development of this computation were not still very good. And we did it with FastWind, that is a spherical non-LTE line blanketed model, and then also the non-LTE considered for the line formation. The other point is that they use photometric calibrations to derive the stellar parameters, and we did a self-consistent spectroscopic approach. I'm going to talk about this now. And then the other thing is that the data set, the spectra are different, and then we use different lines because we had larger coverage in spectral range. Okay, this is a very important step because when we are determining the stellar parameters, we are fixing the properties of the atmosphere in the zone where the lines are formed. And then with these properties, we are obtaining the line formation, or we are obtaining the lines we are going to use for the abundances. If we use photometric calibration, to say it in a roughly way, we use photometric indices. So it's like we are taking into account the atmosphere as a global thing, while in the spectroscopic approach, we are using lines obtaining from model atmospheres to derive the parameters, and then the same models are used for the abundance analysis. So this way is we are better determining the properties of the atmosphere, while this can be dependent of the calibration and other things. This is a good way to do things for cooler objects, but for hotter objects this can be dangerous because we have some kind of degeneration in these indexes. Okay. So taking this into account, we decide to do a new analysis of the B-type stars in Orion OB1. Here I plot you all the stars studied by Cunha-Lambert. We could observe some of them. Which are the questions which motivate our study? The first one is to see if the abundances of the youngest generation of stars are affected by this supernova contamination, or the abundances are uniform. If the abundances from obtained from the star, the study of the star, are in agreement with the nebula or not. This is very important because we are obtaining abundances with two different objects, two different methods. So if we have agreement, this is very important. And if it's possible, we wanted to study if it's possible to obtain constraints on the dust depletion by comparing these abundances. And then the final thing is the following. The chemical abundances of the Orion Nebula and the B-type stars in the solar vicinity, or B-type stars in Orion, can be considered as representative of the abundances of the present-day abundances of the interstellar medium in the solar vicinity. So we can compare this with the Sun, and we can see if they are the same. If we can study some kind of evolution of the solar neighborhoods during the age or the life of the sun. Concerning this, our knowledge about B-type stars in the solar vicinity until a few years was the following. In the case of B-type stars, the different studies obtained highly and homogeneous abundances. I use this plot, very nice plot from proceeding by Thierry Morel, where you can see these are the abundances of B-type stars from different authors. So it's a compilation of all the different abundances obtained during maybe 10 years. And these are the values of the sun derived by Greves and Soval in 98. This was considered as a standard reference for many years. And you see that first, the abundances of B stars are quite inhomogeneous, so the dispersion is quite large, and then the mean value seems to be lower than the solar abundances considered by or obtained by Greves and Soval. But in the last years, there has been a change in this result. The first one is that in 2004, Asplund reviewed the oxygen abundance in the sun, and obtained this value here. And this was like the beginning of what has been called the solar crisis. That is, a lot of people in 3 years, 2 years, begin to obtain abundances of the sun going up, down, up, down, up, down. So we have all these references here. I will show you before. But the thing is that now the abundance of the sun, or the abundances derived for the sun, are in this range. So the dispersion between different authors or different hypotheses in the calculation is this. On the other way, with the good quality spectra now we can obtain, and the improvement in the model atoms in the stellar atmosphere, we have this very nice paper by Prisvilla and Fernanda Nieva, in which they analyzed 6 B-type stars in the solar vicinity with a very similar method to the one I'm going to present you now, and they obtain a very narrow distribution of abundances, and the mean values are more metal-rich. So now we have the dispersion here is large, the mean abundance is lower, this is a bit higher, so are more or less in agreement, but we are going in the right direction, but there are some things can be done. Okay, so the last motivation is to study if the solar abundances are similar or different to those given by the B-type stars and H2 regions in the solar neighborhood. Okay, so here I begin the new study. We obtain a very good quality dataset, observational dataset. Here I show you 3 of the spectra. Is from 3,700 to almost 7,000. So you can see a lot of lines. Here in red, I show you the spectral range observed by Cunha and Lambert. So we have many more lines, and then these are the hydrogen lines. We have also helium-1, helium-2 lines, silicon, oxygen lines. Okay. We decide to do the analysis with the spectroscopic approach. So we are only going to use spectral lines to characterize the stellar parameters and then the abundances. So I want to show you here which are the best candidates to obtain these parameters. Here I show you the behavior of the equivalent width of helium-2 lines, helium-1 line, then silicon-4, silicon-3, and silicon-2. The B stars are from here to lower temperature. So you see that the helium-2 lines, normally used to derive stellar parameters in the case of O stars, is not very good because we are in the limit. Then we have always the silicon-3 line, and depending on the temperature, we can use the silicon-4 line. So we have this ionization balance, silicon-4, silicon-3 for the hotter objects. And then here we cannot use the silicon-4 lines, but we can use the silicon-2 lines. So we can derive with the same atom the stellar parameters. Okay, and here I show you the behavior of the oxygen two lines. Here I'm going to present you results on silicon and oxygen. So this is why I also plot this, to show you that the behavior is, we have the maximum at this temperature, and then it's going down this way and this way. Okay, so this is the spectra. Depending on the temperature, we see that, for example, for the hotter object we have the silicon 4, but not for the cool objects. And then the silicon 2 is the opposite. And then for the hotter objects, we can still see some helium 2. So we have another constraint for the temperature. Okay, so to summarize, to derive the stellar parameters for the hotter objects, silicon 4, silicon 3, this is the behavior of this line ratio that is commonly used to derive abundances. So here I plot you the different behavior for different gravities, because we have different parameters that are related and has to be determined all together. So depending on the gravity of the models, we obtain different temperature. Okay, this is the equivalent width, or the ratio, the observed ratio, and then also the errors. So we have this. Now we go to the hydrogen lines, and we can fix the gravity, because the winds of these lines are very, very dependent on the density and the gravity. So you can decide between these different possibilities. Okay, is this one here. For the hotter objects, we can also use the helium 1, 2. Here I plot you the hydrogen lines, and then the helium 1 and helium 2. So we can do the same to fit this ionization balance. And, for example, for this star, this is the values we obtain for the hydrogen-silicon analysis, and this is from the hydrogen-helium analysis. So you see that the agreement is quite good, and this is a very good thing. For the cooler objects, we need to use silicon 2, silicon 3. This is the behavior, again the same, and we can derive the temperature. Okay. This gives a first idea of the parameters, but we have other parameters we have to take into account for this analysis. The first one is the silicon abundance, and then the other one is the microturbulence, that is a free parameter that is needed to be included in the abundance analysis. So here I show you briefly some important ideas. You can construct this for different abundances, for one line, different abundances, you obtain the equivalent width for different microturbulence. When you have your equivalent width observed and the errors, you have for every one of the microturbulence abundance. So you plot this kind of diagrams with the equivalent width or the line and then the abundance. Depending on the microturbulence, you obtain different abundance. If you do this for different lines, then you see that depending on the microturbulence, you can have a slope in this diagram, or you can obtain the same abundances for all the lines. So this is what you are looking for. So also microturbulence and silicon abundance has to be accounted for in this analysis. Okay, I showed you that we use these two lines, but we can use many more lines because we have many more lines. So actually what is done at the end is this. So we create these plots that are like the other ones with the silicon abundance for each one of the stars. So for example, here you see the silicon 4 lines and the silicon 3 lines for this temperature here. These are the two lines we used previously. We need to increase the temperature to obtain the same abundance for the different ions. Okay. The other important point is that we did a detailed analysis by multiplex. That is, we study what is the behavior of the different lines, because maybe we have blends or problems with the model atom, or who knows. So for example, I want to show you two examples. One is, here is the lines we consider reliable for the analysis, and these are lines that we know have problems. So for example, this is now a long time ago. So for example, in this case, these lines are formed in the upper part of the model atom, so can be affected by boundary conditions and these kind of things. So with this, we can decide the best lines to do the analysis. With this type of analysis, we discovered that the silicon 2 lines normally used to derive the temperature were probably wrong in the model atom and the silicon model atom we use. So for example here, so these are 3 different stars with different temperature. Here we have silicon 3, silicon 4. Here we have the cooler object, silicon 3, silicon 2, and we see that for silicon 2 we have 2 different sets of abundances. This is the line usually considered, and this is another one that is normally not observed. So we see that we can obtain 2 different silicon abundances and temperature depending on the lines. And I don't want to say much about this because this is too detailed for the talk, but there are many reasons to think that the good lines are not the common lines but the other lines. So for example here where we have silicon 2, 3 and 4, we see that the good value is this one and not this other. Okay, if you want, you can ask me about all these details. Okay, so here you have the summary of results for the stellar parameters and the abundances. The different targets from B0 to B2, depending on the temperature, you see silicon 4, silicon 3 lines, or silicon 2, silicon 3. Here you have the results obtained with the different lines, we believe on this. And then also for the hotter object, we have the helium temperatures. So these are the adopted values, basically these that are in agreement, and then for this we take this one. And we see that the abundances here, this is for silicon, are quite similar. These are the uncertainties due to the dispersion in the different lines, and then the microturbulence. So we have that we have a mean value of 7.5, and then the dispersion is about this. For oxygen, we can do the same, but the only difference is that now we have only oxygen 2 lines, not oxygen 3 lines, so or oxygen 1. So we have to rely that the ionization balance is correct. So we have to believe in the stellar parameters we derive with the other element. So here, okay, we obtain the abundances, and for the uncertainties we take into account the errors in the measurement of the equivalent width, then the effect of the microturbulence, the line dispersion, and also this uncertainty due to the stellar parameter determination. So for example, here I show you 2 cases. One is a hot object and the other is cool object, so we are in this range here and this range here. If we change the temperature in this case, the abundance we derive is moving up if we move up the temperature, and is going in the other way for the cool case. So if you don't derive correctly your stellar parameters, your abundances of oxygens can move a lot in any of the direction depending on the star. As we are obtaining the parameters with the spectral line, so we are characterizing the line formation zone with the spectroscopic constraints, we are sure that the stellar parameters are more correct than the photometric stellar parameters. Okay, so this is the result for the oxygen. So again, the dispersion is not very large. The mean value is 8.73. And here I show you what happened if I change in the models the temperature by 500. So you see that until this temperature, so the hotter object, if you change the temperature, you are moving in this way, and then it's the opposite for the cooler objects. Okay, so now the results. The first thing is the comparison with previous analysis. These are the new stellar parameters in comparison with those obtained by Cunha-Lambert. So you see that the green, the red dots are Cunha-Lambert, and the green are the new results. So you see that the difference in the stellar parameters are not negligible. For example, I show you here the case of this star. This one is with the stellar parameters I derived, the other is with those of Cunha-Lambert. So you see perfectly that the gravity is not fitting the lines. So this can be, this is going to affect the abundances. So the thing is that you need to do the abundances with the same model, with the same stellar atmosphere model, you obtain the parameters. If not, you are mixing things. And this change in the stellar parameters is affecting enormously the abundances. So this behavior, this is oxygen, this is silicon, they obtain a large dispersion. They obtain that the higher values for oxygen also correspond to higher values in silicon. This was interpreted as this supernova contamination, but with this detailed analysis we see that all the values we obtain are within the uncertainties of the method. So this is very, very important. Okay, now one of the results is that the abundances in Orion are more homogeneous than previously determined. Here I show you the first diagram with the abundances derived by Cunha-Lambert. These are my previous results, and these are the new results. So you see that these lines correspond to the dispersion in abundance, and these correspond to the uncertainty, to the intrinsic error of the method. So your dispersion is smaller than the errors, but you have to take into account that the errors are the errors. So the abundance of this star can be here or here. Okay, for example, if I compare the abundance obtained with the new data set with the old one, you see that the abundances are different. So the same person, the same star, the same model, the same stellar atmosphere model obtain different results. This is produced by different effects in how you reduce the spectra and other things. Okay, so this is one important thing. With the results, I cannot say anything about any contamination by supernova. These are homogeneous. I can compare with the results by Brisbilla of these 6 unevolved objects in the solar vicinity, and we obtain the same main value, the same dispersion. This is very good. So it seems that all B-type stars in the solar neighborhood are giving the same value, and the dispersion is not as large as previously determined. So maybe this dispersion was due to uncertainties, to errors in the analysis, and now we can do things better. And this is very funny because I plot here the different results obtained from, the first one is the solar value by Greves in 98, and this is from the new determination of Asplund in 2006 to 2008, 2 years. Okay, they need to discuss and decide. Nicolas told me that they have I think it's a review, I don't remember now in which journal, with new abundances, so it's very interesting to see what they are saying in the last paper or in this review. But the thing is that now we are within the uncertainties. We cannot say if the sun is up or down compared to the B-type stars. Okay, this is taking into account the uncertainties, but if we relied on the mean values, because the statistics in the B-type stars now are increasing. Okay, taking into account chemical evolution models, you expect that from the time the sun was formed to now, you have evolution of the solar vicinity, so you expect to have higher values by 0.13 or less, depending on the model, in the cases of oxygen. So if we believe in this mean value of oxygen abundance, the solar value should be over here. So it seems that the value obtained by Asplund, that I think is very close to the one described by Greves in the last review, seems to be correct. So we are going in the right direction. This is the same for silicon. The first very, very important result is that now this huge discrepancy we had in silicon is disappearing. Probably this is due to the way the abundance were determined, so photometric indices, and also maybe the model atom. And again, the mean value is very close, is practically the same as Priscilla, and the Sun is also here. So the Sun and the B-type stars have the same abundances, are not subsolar anymore. Okay, this was submitted 2 weeks ago, and now some things can be done about the comparison with the nebula. So here I show you the last result, and now we have again the recombination lines, the collisional excited lines. So we can have, very good agreement with the recombination lines and a small amount of dust, or larger amount of dust, and these are the good values. So we have to study dust depletion to try to understand what is happening here. Okay, it's possible to find constraints on the abundances of these elements. Okay, I found a paper by Drain proposing different type of composition of dust. This is very uncertain, so but we can consider these different possibilities. So we have silicates, different type of silicates combining in different forms. So we can consider first this or a combination of this. Then we have the oxide of magnesium and iron, and we can consider this. So we need to study silicon, magnesium and iron abundances to then see the amount of oxygen depleted onto dust. In the case of the stellar, this is easy. In the case of the nebula, it's not so easy for some of the elements. So for example, for oxygen we have many lines. We have collisional excited lines and recombination lines, so we have to take into account this difference. For silicon, it's not so easy. There are only 2 papers deriving silicon abundances in Orion. These are Rubin and Garnett. They use these interrecombination lines or intercombination lines in the UV, and then they need to use some ICF, some ionization correction factors. So the way they obtain this silicon is they obtain the carbon abundance and then relate the silicon with the carbon and then apply an ICF, and so it's not so easy. Or we have the other possibility: silicon, then silicon with carbon with the ICF, and carbon with oxygen, and then oxygen. But then for the oxygen we have the collision and excited lines, the recombination lines. So again, for magnesium we need photoionization models, and for iron it seems that it's easier, but you have to take into account a few things. Okay. For example, for the case of silicon, as I showed you, these are the stellar values, and these are the silicon values obtained in these 2 papers. This is the collisional excited line by Rubin, and these are the 2 options proposed by Garnett, depending on if you consider a T-square scenario for the oxygen abundance determination. So it's this or that. So it's not so easy to obtain constraints for the dust. Okay, but let's play a bit. For oxygen, we have this. Silicon is not here, but 7.5. This, we are working on the determination of these abundances for the stars. And now for silicon, we have to consider all the cases and see what happens. So different abundance for the silicon, the magnesium, and different possibilities. Okay, so as we have seen that the oxygen and silicon abundances in Orion stars are very similar to the ones studied by Priscilla, we can use the values for the magnesium and iron. We don't expect to obtain different results, and in fact this is what we are obtaining. And we put all this and all this. We play a bit, and curiously we obtain that the amount of oxygen expected to be locked in dust is between 85 and 120 parts per million, and these are the uncertainties. And what is curious is that these values are independent on if you play and you decide, well, the fraction of this and this is different, finally you go to the same result. So this is just to see what happened. If we consider the abundance of B stars, taking into account the uncertainties, and we obtain the dust, the oxygen in dust, this is the possible range of values for the nebular gas. So it seems, also it's not we are investigating this, that the collisional excited lines are given to low values. But this depends on a lot of things. Okay, so concluding, we have done this very detailed analysis, and we have found important discrepancies on the stellar parameters and the silicon and oxygen abundances compared with previous results. Now the derived abundances are more homogeneous, coherent with other B-type stars in the solar vicinity. And we have compared with the solar abundances. This now we can say a bit more, try to investigate a bit more, and also with the Orion Nebula, taking into account the dust depletion scenario. So thank you very much.
Now we have some time for questions. Please remember we are streaming this seminar, so please don't ask the question until I have given you the microphone. Otherwise, the people online won't hear it. So, any questions?
Thank you. That's an exceptionally interesting presentation, if I may say so. And it seems to me the weakest part, not of your presentation, but of what people think, are the galactic evolution models. That is to say, the fact that the Orion Nebula abundances agree with the solar abundance or some model says they should disagree by 0.13 dex. Too bad for the model, I think. I think the things that have to be revised are the models now, those models, the galactic evolution models. I think that your data and the way you use it are now getting very good and show that basically there's very interesting to show there's no difference in abundance between the Orion Nebula and the Sun, which is something that goes completely against what people were saying for about 20 years. So that's very good.
Now, I think now very difficult because people have said that there can be a lot of radial migration in the galaxy. So the fact that the Sun is now what it is doesn't mean that it didn't form somewhere else. So kind of difficult to predict what should be the mentality of the Sun. Well, also that it has to have been chemical evolution, but to predict the radial migration of the Sun is very difficult because the kind of migration depends on. Yeah. Okay.
Any more questions, comments?
I have my point is that Orion is not a quite active region. Orion is quite active region in terms of formation of stars. So why we should expect in our solar neighborhood is not? So why we should expect the same abundances? Because if there is a stellar formation, there is feedback.
Yeah, it's true, but for example...
Stars, these are young stars, so these stars are forming out of this medium that is supernovas around. I won't be surprised that there will have been a contamination by supernovas. You show that it seems not to be the case, but it does not look...
No, but the one important thing is that we have to move our ideas to the observation, not the other way. So, for example, in the case of the Sun, so now one important thing is the mean values, but also the uncertainties. So it's important to say, okay, because if you now obtain this value for the B-type stars, and now the Sun is lower, you can say, some people say, no, but it's because the Sun is moving from inside the galaxy to this point. So the interpretations can depend on this. Also, okay, you expect to have oxygen and silicon contamination in the Orion Nebula because you have features of supernova in all this region, and it's true that you have different ages, but the observation say that this is not appearing. So what happened? That maybe there are other explanations. For example, one proposed by Guillermo Tenorio that the elements when explode from or when it goes out from the supernova goes outside the galaxy, and then you have like a rainfall. So maybe the time passed from the formation of the first star to the last stars in Orion is not enough to make these elements come back. So the thing is that you have these different possibilities. And now you have to go to the observation and say, this is what we have. The observation are what are. And now you can explain. But you cannot try to, okay, we expect contamination, so it's the observations are there, and we have to take into account the mean values and also the uncertainties in this. So I'm not saying, I cannot say if you have contamination or not. It's within the uncertainties. Maybe I did something wrong, and then abundances are moved up again and down in the younger, in the older stars.
Anyone else?
Okay, you are comparing the B-type stars with a solar-type star. Okay, what's the comparison for stars in Orion? Actually, can you compare B-type stars with solar-type stars abundances in Orion? We have done some work in Orion OB1, okay, and Sigma Orionis in particular, where we find solar abundances in general. But what happens in Orion OB1? They find
solar abundances.
We define solar abundance as the relative abundance to the sun. Basically, we find the same abundances than in the sun. You don't know the abundance of the sun. You don't know the abundances of the B-types. We rely on models. It's not only that you have good spectra. Anyone use models, okay? So we rely on the ability of the models to describe the photospheres. I will trust a comparison of models for O types and solar types because they come from very different physical fundamentals, okay? So that's the base of my question. When I compare the solar type stars in Orion with the sun, I find the same values for the same model, okay? Doesn't mean that we have the right level.
So it's relative. So you analyze the sun and then
but I'm comparing the same kind of stars and using similar models. Mm-hmm. Now you are comparing and if you find the same thing. But I was curious to know what happens for the solar type stars in Orion OB1. Is it known? It's basically whatever, yeah, okay. Not for oxygen. We have not done oxygen. But silicon, you take basically what you infer from the Kurutz model in the sun, which I don't remember now, and you find the same value for the same lines in these stars in Orion OB2, okay? I don't have in mind the numbers. You could check that in González Hernández last year. But I think this is the right way to proceed, okay? I'm not criticizing your procedure. It's just that you may be interested to compare with the stars of low mass in your stellar association and see where you find the same kind of abundances.
In fact, for silicon, this is one of the things I'm now interested. So, for example, for silicon, as you said, if you have the same abundance as the sun, and the sun, the only values are more or less this, so we are in agreement. And for oxygen, I'm very happy that Jona is coming, because I want to propose him to do this the same as the nebula, but for because I haven't found any oxygen abundance determination in solar type stars in Orion. So I think this is a good study. I don't know if there is any or not, but
it's just to make a small point on that. Remember that 10 years ago, the problem was that the oxygen abundance derived for the sun was larger than the oxygen abundance derived for B stars in the solar neighborhood, which was quite a problem for all the comments. So this is now away. This is not the case anymore. And the second point I would like to emphasize in view of the discussion is that what this work shows is that there is no contamination when comparing B stars within Orion. There is no sequential contamination of the B stars in Orion because of supernova contamination, etc. Not comparing to the sun, but comparing within Orion. The different regions in Orion have a uniform composition. So the sun here is used only to, say, as a global comparison of a more general comparison. But even in that respect, the situation has improved a lot in the last years.
It's still remarkable that you cannot distinguish the abundance, but the abundances are within the limits of all measurements now the same.
Yeah.
It's a completely remarkable result. I agree, and I don't have any particular theory to support it. All I can say is that everybody who's been producing theories to show that that shouldn't be the case must be wrong.
I mean, it's quite surprising too, right? I mean, because of very different environments, so it's different environments.
Okay, so I think we should thank again Sergio and everyone here.